Okay, so let's review some trig graphs. First of all, we have here the graph of y equals sine of x. And let's just review some features of this. So the domain is all real numbers because it goes to the left and right forever in both directions with no breaks or anything like that. And if you think about what the sine function is, the sine function tells you if you start at the positive x-axis on the unit circle and you rotate around some number of radians, either counterclockwise in the positive direction or clockwise for the negative direction, this function is graphing where you end up at your y-coordinate. So no matter how many times you run around that circle, you are still going to have a y-coordinate between 0 and 1. And there aren't any numbers, any real angle that you could have that doesn't have a corresponding y-coordinate. For any real number that you can come up with, I can find the corresponding y-coordinate by starting in the positive x direction and turning that number of radians, whatever it is, around, and then measuring the y-coordinate of where I end up on the unit circle. That's what the sine function does. And this is a graph of, as you move around that circle, your y-coordinate moves up and down. Okay. We can do the same types of function transformations to this sine function as we could to any other kind of function. Absolute value, y equals x squared, square root of x, any type of function that has kind of a recognizable shape will have that shape change in the same way when we do certain things to that function. So I'm going to illustrate some of those changes by taking this graph, which is y equals just plain sine x, and turning it into this graph of y equals -2 sine of 1/2 x minus 3. So the first thing that I want to deal with is the fact that we have this negative sign in front. I'm writing in pencil because I'm going to kind of draw some stages as we go, and I want it to be light so that the graph doesn't get too cluttered. So negative in front means that we reflect over the x-axis, aka turn upside down. So every point on this original sine graph, the negative sign in front is going to basically flip this whole thing upside down and create the same shape. Oops. Just in the opposite direction. So this is negative sine of x. The next thing that's happening is that we have a multiply by 2 in front, which is a vertical stretch. So what this means is we're going to get twice as high. I'm sort of getting close to the words up there, but it's okay, because this isn't gonna be our final destination. So I'm going off of the last step that I had. Now I'm drawing a graph that is twice as high. This is the graph of -2 sine of x. So I'm kind of adding in these changes one stage at a time. Next, I'm going to do the -3. Technically, the order doesn't always matter, and we could do the 1/2 first, but that one's going to be the trickiest, so I'm going to save that one for last. And instead, I'm going to follow this -3. So, -3 on the end means we move down 3. And now we need to be careful not to just count 3 boxes, because if we look at our scale here, each one number that we change on the scale actually includes 2 boxes. So if I'm going to move down 3, that means I'm actually moving down 3 of these tick marks, or 6 boxes. So 1, 2, 3, 4, 5, 6. Moving this point down to here, moving this point down to here, and moving this point down to here. I'm moving this point down to here. Oops, I skipped this one. I'm moving this point down to here. So each of these points on this most recent taller graph that I drew, I'm moving down 6 boxes in order to follow that vertical shift. So now I'll draw this graph in. Okay. So we're almost there. This right now is the graph of y equals -2 sine x minus 3. And the last thing that I have to do is this 1/2 change x to 1/2 x, or multiply x by 1/2. And this is a horizontal stretch wider by 2. So this might seem a little bit counterintuitive. You might remember the rules that the stuff with x kind of always happens in the opposite way that you expect. We can also think about this in terms of our equation that says that the period is 2 pi over k, and this k value is 1/2. 2 pi divided by 1/2. Dividing by a fraction is the same as multiplying by its reciprocal. So this is 4 pi. So we went from a period of 2 pi to start off with to a period of 4 pi, which matches up with what we saw earlier in the year, that if you multiply x by a number less than 1, it results in a horizontal stretch. Or you could also think about this as x divided by 2. Either way, it's a horizontal stretch. So what this means is that each point on this graph is going to get twice as far away from the y-axis. It's going to kind of expand from here. So, for example, this point is going to move to here. And this point is going to move to here. This point is going to move all the way over to here. And this point is going to move, it's at 3 pi over 2, so it's going to move all the way over to 3 pi. Okay, so let me trace the shape that we're going to get here, and hopefully that will let you see what I mean by this horizontal stretch. So basically this wave has gotten twice as wide as it did before because of the 1/2 x. So the rules that I use to figure out this sort of progression of changes are the same transformation rules that we used earlier, but you can also do it a little bit more quickly just by learning some of the general rules that are more trig function specific. So for example, this number is called the midline, and that tells you the sort of middle y value of the graph. And we can see that -3 does go through the middle of our wave. This number is called the amplitude, and that tells us how far above or below that midline we get. So from -3, we go up to -1 and down to -5. That's the range of our function, and we got that from starting at the midline and going up and down by 2. And then the fact that it's a negative and a sign tells us that we start at midline going down. And then we already kind of used our period rule to help us interpret this horizontal stretch a little bit. So you can think of these changes to the equation as being just like other function transformations, or you can learn the trig specific rules that say this number is the midline, this number is the amplitude. If it's a sine wave, that means it starts at the midline. If it's negative, it means we start by going down. And then this equation, the period is 2 pi over k. K, you might remember, has the special word angular frequency, but you won't ever be tested on that. Okay. So hopefully this kind of made sense so far and let you see how the different parts of the equation affect the graph. Now that we have the graph in front of us, let's look at a couple of other things. So if this is my function f of x, -2 sine 1/2 x minus 3, then I might want to know, where does the function reach its maximum value? And we see 2 places, right? I could put it at x equals -pi, or I could write x equals 3 pi. Either of those are x coordinates where the function reaches its maximum value. But even though those are the only 2 that I can see on this graph, I could continue the graph and I would see more of these as the graph continued. So this is not quite a complete answer, even though it looks like a complete answer based on what we can see of the graph, just this portion. But the rule of what you do is you can take either one of these, it doesn't really matter, any individual example to start with. So let's just use 3 pi. Either way, it doesn't matter. And then I'm going to add the period times n, and I'm going to say where n is any integer. Meaning I could add any multiple of 4 pi to this original x value to find another location where the function reaches its maximum value. We're going to do a similar thing for this question. On what intervals does this decrease? So I see that I have one decreasing interval that is from negative pi to positive pi, right? From this x value to this x value, my function is decreasing. And notice these are not less than or equal to's, they're just less thans, because I couldn't say that the function is decreasing at this point. It's turning around there instead. Or in interval notation, I could write this as negative pi pi. This is a little bit confusing because we use the same sort of symbols to specify like an x and y coordinate, but here these are indicating an interval and not an x and y coordinate. But that's why I like to use this one, because I think it's a little bit clearer. It has less of an overlap with other notation. But we're going to do the same thing that we did for this answer about the maximum values. This is not the only decreasing interval. We can see another interval starting here, and we don't see the end of it, but we know it is going to turn around in a little bit. So we want to do 4 pi times n, the period, whatever the period is of this individual function, times n on each of these numbers. So negative pi plus 4 pi times n is less than x is less than pi plus 4 pi times n. This is a more complete answer because it's not just one example, it's starting from one example and then basically adding this repeat every 4 pi instruction. So this is basically saying we have one interval from negative pi to pi, and then that same behavior is going to repeat after 4 pi units every time. Okay, what's the range of f of x? We already know that the domain is all real numbers because we can see that it's, anytime you have sine or cosine, the domain should be all real numbers. But the range is from negative 5 to negative 1, or we could write this in interval notation as negative 5, negative 1. I'm using with the equals or square brackets because the function does actually touch those y values. It doesn't just come close, it does actually touch those y values. Okay. And then lastly, is this even, odd, or neither? So, there's lots of ways to think about this even, odd stuff. For trig functions, you can remember the rule that sine is odd unless it has something added or subtracted, in which case it's neither. So this is going to be neither. Or we could get a little bit more advanced than that and think about the rules for even and odd. So if something is even, and I have a point x and y, then that means that if I change the sign of the x coordinate, I should have the same y coordinate. So if this point is part of the graph, this point should also be part of the graph. If it's odd, then if I have a certain point on the graph, if I change the sign of x, I should get the opposite sign, y. Let's take these 2 points as a comparison. This graph has the point negative pi, negative 1, and it also has the point pi, negative 5. These are these 2 points. These points have the same x, just with opposite signs. And then we want to say, do these have the same y? Do they have opposite sign y? Or are they just not related to each other? And when I compare these two x's, one is negative pi, one is positive pi, the y's are just two completely different numbers. They're not negative 1 and positive 1. They're not 3 and 3. They're not equal, they're not opposites, they're just two different unrelated numbers. So that means it must be neither. Our original sine graph is odd because if, for example, you wanted to look at this point and this point, this is the point pi over 2, 1, and then this is the point negative pi over 2, negative 1. So when I change x to be the opposite sign, y is again the opposite sign. These 2 points sort of go together. And any point that I choose is going to have a corresponding point with the opposite sign of x and the opposite sign of y. So, for example, if I wanted to pick, I don't know, a point over here, this would be, this is pi over 4, so 9 pi over 4. And then this vertical thing would be the square root of 2 over 2. If I were to extend the graph further over to the left, I would also have the point negative 9 pi over 4, negative square root of 2 over 2. I can prove that to you if you want. So, put myself in radian mode. Sine of 9 pi over 4. This is indeed the same number as the square root of 2 over 2. And the sine of negative 9 pi over 4 is the negative of that. So I changed what was on the inside to be a negative, and I got the negative answer outside as well. That's what it means to be odd. Cosine is even, and cosine remains even if you add or subtract a number to the end. What that means is if you change the sign of x, you change it from a positive to a negative or negative to positive, you will get the same y value and not the opposite or negative. Okay. Hopefully this made sense. Hope it was helpful. Let me know if you have any questions. It's pretty easy to reach me over email or Remind. I answer pretty quickly. So if you are having trouble with any of this, please contact me. I will talk to you again soon.